Welcome to the fourth video in the FISAB training series on European fire safety regulations for sandwich panel products. In this video, we will explore key engineering considerations and solutions that enhance the fire safety of sandwich panels in building design. Fire stops are critical materials or assemblies designed to seal any openings or joints in a building structure to prevent fire and smoke from spreading. When a fire breaks out, fire stops perform several essential functions. First is containment. Fire stops block the spread of fire and smoke through gaps, helping to keep the fire contained within a specific area. Next, structural integrity. They help maintain the strength of fire-resistant barriers, ensuring that the structure continues to protect the building, reducing the risk of early collapse or failure. Some fire stops also provide thermal insulation, slowing heat transfer and protecting adjacent areas. Finally, it is important that fire stop materials are elastic enough to expand back after compression. This flexibility lets them adapt to panel movement in both normal and fire conditions, keeping the seal tight and effective. This slide shows the top connection of sandwich panel walls in fire conditions. For tall panels, the suspension fasteners can either be positioned locally at the edges of the panel as shown in the left figure with point suspension, or they can be distributed continuously across the entire width of the panel, shown on the right with continuous suspension. In the point suspension setup on the left, suspension loads are carried by short cleats. This design gives the panel some flexibility to expand under heat without compromising the overall structure. With continuous suspension, the loads are carried by angles along the top of the panel, securing it more rigidly. While this design prevents free expansion, it provides a more stable connection across the entire width. Both configurations include fire stops. These fire stops are crucial because they fill the voids along the panel edges, creating a seal to prevent fire and smoke from spreading. Fire stops need to be resilient enough to maintain the seal for the entire duration of the fire. This slide illustrates the top connection of sandwich panel walls in fire conditions, showing both horizontal and vertical installation setups. On the left, we have the horizontal installation. In this configuration, several components like the sealing band, fire protection wall, and spike fasteners work together to provide fire safety. The fire protection wall, highlighted in red, is mechanically fastened to the surface and helps insulate against heat transfer in the event of a fire. On the right, we see the vertical installation. Similar components are used, such as the sealing band, mineral wall, and fire protection wall, each serving to reinforce fire resistance at the top connection. A critical consideration here is that during a fire, the panel wall's dead load must be supported from the top. This means the fasteners to the roof or ceiling must be specifically designed to withstand this load, as the panels will effectively be hanging from the top when exposed to high temperatures. Overall, these installations use fire-resistant materials and strategic fastening to contain fire spread and maintain structural integrity in critical areas. In this example of fire stopping for service pipe penetration, a hole is cut in the panel to pass the pipe through. The gap is filled with non-combustible material like stone wool and sealed with fire protective mastic, such as an intumescent, to hold everything in place and prevent damage in case of pipe movement. A collar made of steel sheet or fire protective board is fastened around the opening. If the pipe is made of steel, it needs external insulation for about a meter on each side to limit heat transfer. For thermoplastic pipes like PVC, an intumescent collar is used instead, which expands to seal the gap as the pipe melts in a fire. An alternative setup for fire-resisting panels includes a non-combustible sleeve that extends at least a meter on each side, with the panel core sealed by fire protective mastic. This slide focuses on the fire-rated joints in steel-faced sandwich panels. Most of these panels use interlocking edge joints, which rely on a substantial overlap to stay secure under fire conditions. A larger overlap at the joint reduces the risk of separation or distortion caused by heat. For longer panels, mechanical fastening may be needed to keep the joints from opening. This is specifically important when using panels longer than those originally tested for fire safety. Let's consider a scenario where a sandwich panel ceiling is exposed to a fire below. As the fire intensifies, the gas temperature at the ceiling level rises significantly. When this temperature exceeds the debond temperature of the lower facing, a critical failure mode can occur. The lower facing can detach from the core material, potentially falling and becoming a hazard for firefighters and occupants. To mitigate this risk, it is imperative to carefully consider the fire design of the fastenings at the panel ends. These fastenings must be able to maintain their integrity throughout the entire fire resistance period of the ceiling. By ensuring the proper design and installation of these fastenings, we can significantly enhance the overall fire safety performance of sandwich panel ceilings. Now let's consider a different scenario where a fire occurs above a sandwich panel ceiling. As the fire intensifies, the heat rises and can penetrate the ceiling void, potentially reaching the underside of the sandwich panels. This scenario highlights the importance of proper fire compartmentation. If the void space is not adequately sealed, the fire can spread rapidly through the void, compromising the fire resistance of the ceiling. In severe cases, the heat can cause the panel facings to delaminate and fall, creating a significant hazard for firefighters and occupants. This is depicted in the figure where the panel faces are shown falling downwards. To mitigate this risk, it is crucial to ensure that the fire resistance of the ceiling system, including the panels and the void space, is adequately designed. This may involve the use of fire-resistant materials, effective sealing of joints, and appropriate fire-stopping measures. Additionally, the fire design of the panel and fastenings remains critical. These fastenings must be able to withstand the elevated temperatures and maintain the structural integrity of the ceiling throughout the fire resistance period. This slide highlights a critical fire safety concern in buildings with sandwich panel ceilings: the potential for unseen fires to spread undetected. The fixing of the ceiling is very critical, especially for the purpose of evacuation and firefighter safety. As you can see on the figure on top, the fire can originate within a concealed space, such as a service void, and spread rapidly without being immediately visible. In the event of a fire, temperatures can soar to extreme levels, reaching 600 to 1200 degrees Celsius. During such intense heat exposure, it is crucial to ensure that the sandwich panel faces remain supported. To achieve this, we must employ secure support systems, for instance, hangers and inverted T-section members could be used as depicted in the figures. These components must be securely fastened to both faces of the sandwich panel using mechanical fasteners. This connection prevents the panel faces from falling, safeguarding lives and property. In the case a scenario where a sandwich panel external wall is directly exposed to fire, as you can see in these figures, the fire can impact the wall from both the inside and the outside. When exposed to fire from the inside, the heat can cause the adhesive bond between the core material and the outer facing to weaken and eventually fail. This can lead to the detachment of the outer facing, which may be carried away by the wind. Additionally, the wind can worsen the situation by increasing the heat transfer and creating a suction effect that can pull the outer facing away from the core. On the other hand, if the fire originates outside the building, such as a nearby fire or a fire in a neighboring building, the intensity of the heat and radiation can also cause the adhesive bond to fail. Again, to mitigate these risks, it is crucial to consider the fire design of the fastenings at the ends of the panel. These fastenings must be able to withstand the elevated temperatures and maintain the structural integrity of the wall throughout the fire resistance period. Now let's discuss a critical factor that can significantly impact the fire performance of vertical sandwich panel walls, the span length. As you can see in the figures, the fire test specimen on the left has a relatively short span length of 3 meters. In contrast, the actual application on the right shows a much longer span length of 12 meters. The increased span length in reality leads to higher dead loads on the panel, which can put additional stress on the top fastenings. During a fire, these fastenings must carry not only the dead load, but also the increased loads caused by thermal expansion and potential deformation. If the top fastenings are not adequately designed to withstand these increased loads, they may fail, leading to the collapse of the panel. This is significant risk that must be carefully considered during the design phase. Therefore, it is crucial to pay special attention to the fire design of the top fastenings for vertical sandwich panel walls with large span lengths. Now for the vertical joints between horizontally installed sandwich panels. As you can see in the figure, the long panel screws play a crucial role in maintaining the integrity of the joint. These screws must be able to resist the forces generated by thermal expansion and contraction during a fire. If the screws are not adequately designed or installed, they may bend or fail, leading to the separation of the panel ends. This separation can compromise the fire compartmentation of the building, allowing fire and smoke to spread. As you can see in the figure, under fire pressure, the panel bends and the screw bends as well, so it forms a bigger gap. In this engineering solution by Ruki, under the flashing, the fire protection material such as stone wool is protecting the long screw, and fire in this case will not easily penetrate to the inside of the panel. For vertical connections between horizontally installed sandwich panels, as illustrated in the figures, a common method involves using self-tapping screws to secure the panels to a load-bearing steel column. However, it is essential to consider the potential impact of fire on these connections. If a fire occurs on the outside of the building, the heat can transfer to the self-tapping screws, potentially compromising their integrity. To mitigate this risk, the screws must be fire protected. This can be achieved through various methods, such as using fire-resistant coatings or by ensuring adequate insulation around the screws. Additionally, the steel column itself should be fire protected, especially on the inside facing the fire. This will help to prevent the column from failing and compromising the structural integrity of the wall. One critical aspect of fire safety in building design is the risk of fire spreading through sandwich panel walls. As you can see in the figures, there are three potential scenarios to consider here. In scenario A, the entire sandwich panel, including the non-combustible core and outer facing, moves away from the fire wall. This can occur if the fire intensity is high enough to weaken the adhesive bond between the core and the facings. For scenario B, the non-combustible core remains in place, but the combustible core is consumed by the fire. This can create an air gap between the remaining core and the fire wall, allowing hot gases to pass through and potentially ignite combustible materials on the other side. In scenario C, a sandwich panel with a non-combustible core delaminates, allowing hot gases to pass through the air gap and potentially ignite combustible materials on the other side. To mitigate these risks, it is crucial to carefully design the junctions between sandwich panels and fire walls. The junction should be sealed to prevent the passage of fire and smoke. Additionally, the fire resistance of the firewall and the adjacent sandwich panels should be carefully considered. A common challenge in fire safety design is the thermal bowing of traditional floors. As you can see in the left figure, when exposed to fire, traditional floors can experience significant thermal expansion, leading to thermal bowing. This vertical movement can disrupt the connection between the floor and the sandwich panel wall, creating a gap that can allow fire and smoke to pass through. To mitigate this risk, it is essential to employ a fire-stopping solution that can accommodate the thermal movement of the floor. One effective method involves using a flexible steel strap to connect the sandwich panel to the edge of the floor. This steel strap allows for vertical displacement, ensuring that the panel remains in contact with the floor even as the floor bows. Additionally, a fire-resistant material, such as stone wool, can be used to fill the gap between the panel and the floor, further enhancing fire protection. By implementing these measures, we can significantly reduce the risk of fire spread through the junction between the wall and the floor. This was it for this video. In the coming video, we are going to discuss reaction of sandwich panels to fire. Thank you for watching and see you in the coming video.